We're going to the moon to explore, and we're going to the moon for scientific discovery.
Watching Apollo footage,
Our destiny is always to go and see what's further and what's next.
The moon is a stepping stone, and the moon is a place we need to learn how to live so that we can continue to go beyond.
Humans will be returning to the lunar surface in 2024 in an endeavour which initiates the new age of space exploration. Rovers will be playing a crucial role in lunar operations as they will be responsible for a breadth of tasks. It is optimal to test these developed robotic systems prior to arriving at the lunar surface in environments that replicate as closely as possible the target destination. Constructing physical implementations of mock environments to test system performance is both a time-consuming process and harbours significant overhead costs. A feasible alternative is the use of a simulated environment. NASA has collaborated with Open Robotics, the team behind Gazebo, to create an end-to-end, high-fidelity lunar simulator for the Artemis mission. This simulator has a very high level of realism. However, its production required significant changes to the back-end rendering system in Gazebo and the creation of custom plugins, none of which are open source. The technology company LG created a high-fidelity simulator for autonomous vehicle development within Unity. Whilst Unity is a game engine and has a focus on visual fidelity, the LG simulator proves that robotic simulation on the platform is achievable. So why do we want a simulator? Well, it's a very convenient and easy way for primary testing of developed systems, and currently there exists no open source solutions with visual fidelity that is analogous to the lunar environment. As a result, this thesis aims to investigate simulating platforms for the creation of a high-fidelity robotic lunar simulator. In creating the lunar terrain, data was first extracted from satellite imagery to provide a general characteristic shape of the terrain. Given imagery resolution is approximately 25 centimeters per pixel, important features of the terrain are lost and must be procedurally regenerated. In Unity, the terrain undergoes processing to smooth artifacts. The default skybox is replaced with a black skybox with no atmosphere, accurate lunar gravity, and a directional light 5 degrees above the horizon. Previous lunar missions show that cameras are also subjected to lens flare, and thus this was also accounted for in simulation. Unity offers a terrain layering system allowing for multiple layers to be sampled on top of each other. The progression of shots here show that as more textures are added at varying frequencies, the repeating tiling effect is eroded and realism is heightened. Small craters were inserted, shadowing was implemented, and rock generation is performed using known size frequency distributions. In Gazebo, a similar process is carried out. A terrain model was inserted and textured, the lighting conditions were created, and rocks were added using an ad hoc method. High visual fidelity of the lunar surface was not achievable in Gazebo as only one texture can be applied to the terrain, resulting in the repeating tiling effect. The incorporation of Gazebo with the ROS ecosystem is well established, with a built-in internal scheduler communicating messages. Unity, however, requires manual configuration of the communicating architecture with ROS. A similar architecture that exists within Gazebo is implemented, with bidirectional communication to a server endpoint that is connected to ROS nodes. The ClearPath Husky rover was imported using its URDF model, which describes the robot's physical description to ROS. A custom controller was built for Unity based on differential drive to accept ROS geometry twist messages and execute them. In comparing the two simulators, a qualitative approach is adopted. In terms of terrain generation, it was possible to replicate the terrain closer in Unity due to its sophisticated terrain generation capability. Challenges were faced with procedural rock generation in Gazebo due to its poor rendering engine and the lack of optimization techniques. And as a result, the rock size distributions in Gazebo are not analogous to the moon. Representative rock size frequency is important for analysis for navigation algorithms, which must account for object detection and avoidance. Unity was capable of accurate rock modeling, therefore aiding in the usability of the simulator for testing navigation algorithms. With respect to simulating lighting conditions, Unity allowed for light intensity changes, varying shadow rendering options, and the addition of lens flare, none of which were achievable in Gazebo. Hardware constraints inhibited the creation of shadowing within Gazebo, impacting its representation of the lunar surface. One phenomenon, known as the opposition effect, was reproducible in Unity, however not in Gazebo. This effect occurs when the viewing angle and illumination angle reach coincidence, resulting in the lunar terrain becoming extremely bright and terrain perception practically incomprehensible. Unity was capable of reproducing the harsh lighting conditions on the moon, which is significant since sensory capability can be tested in the simulator whilst being subjected to similar conditions on the lunar surface. Whilst Unity's robotic simulation community is constantly expanding, the established architecture with ROS is far less developed and streamlined compared to Gazebo, and more manual configuration is necessary. In addition to this, Gazebo has a lot more available community support. Considering all factors, Unity has significantly outperformed Gazebo. The simulator is capable of reproducing key aspects of the challenging lunar environment, making it possible to test performance of developed systems in the simulator. This thesis has contributed a comparative analysis into the simulating platforms Unity and Gazebo, and a state-of-the-art robotic lunar simulating platform in Unity that is easily extensible and open source. The created simulator paves way for future extensions including implementation and analysis of navigation algorithms which are based on sensory feedback, extending the simulator to account for terror mechanics, and the adoption of machine learning to compare synthetic and real imagery. Thank you for listening, and I welcome any questions.